Now we know that the continuity equation is based on the principal conservation of mass. So that what this means is any liquid that is flowing in a pipe, the fluid quantity will be the same from the inlet to the outlet here. Now we are going to derive a continuity equation in 3 dimensions. So to derive this and put it in a mathematical form, let us consider this fluid element. So this is a fluid element of length dx. So this element is length is dx. This will be dy, and here this we'll take it as dz. Okay, in the direction of x, y, and z. So this is the length of the fluid element here. Now let us have the velocity component here, the inlet velocity over here. This is the inlet. Okay, now this velocity component, we will take this particular fluid element as a, b, c, d, e, f, g, and h. Okay, so this is a component of dx, dy, and dz. Now the velocity component is, in the x direction we will take it as u, in the y direction we'll take it as v, and in the z direction we'll take it as w. So u, v, w is nothing but the inlet velocity in x, y, and z direction. Okay, so now first we will take the mass of fluid that is entering the phase A, B, C, and D. So this is a phase A and C, A, B, C, and D. So what is the mass that is entering the phase A, B, C, D per second? So mass of fluid entering the phase A, B, C, D is nothing but, you can write it as rho into velocity in x direction into the area A, B, and A, B, C, D. So this we can simply write here as rho into u into, this is what, dy into dz. So this is nothing but dy into dz is the area of ABCD. It's a cross section area. Okay, now this is a mass that is at the inlet. Of this fluid element. Now at the outlet, mass of the fluid is will be at EFGH. So this is the way the flow is happening in x direction. EFGH is nothing but this particular mass that is entering plus the additional mass that is differentiation of this particular mass. So we can take this as, we'll be writing this as rho u dy into dz plus dou rho u into dy into dz dou by dou x of rho u dy dz in the direction of dx. Okay, so this is the mass of fluid leaving. Okay, this is the outlet here. Now let us take the gain of masses. The gain of mass in x direction will be equal to mass of fluid through AB CD minus mass of fluid that passes through EFGH per second. So that we can write it as rho U dy into dz minus rho U dy dz minus dou by dou x into rho U dy dz to dx. Okay, so what we'll get here is these two gets cancelled, so we'll be getting as dou by dou x negative minus of rho U dy by dz. So this is the gain in mass in x direction. Now similarly, in the gain in mass in the y direction will be dou by dou y into rho into v, okay, v into, so sorry, here I forgot to write dx here, so it will be dx dy and dz. This is in y direction, and similarly in the z direction we'll have it as minus dou by dou z into rho w into dx dy and dz. So the net, and this is in x direction, so the net gain of mass, okay, the net gain of mass in all the direction, we can write it as the summation of all this. So the net gain is equal to, take the minus sign out and we'll write it as minus dou by dou x rho u plus dou by dou y rho v plus dou by dou z rho w into dx dy and dz. So this is the net gain of masses in all the three directions. Now we know that masses can neither be created nor be destroyed in fluid element. The net increase of mass per unit time in the fluid element must be equal to the rate of increase of mass of fluid in the element. Okay, what does it mean is, the mass of the fluid basically so mass of fluid is nothing but rho into dx dy to dz. So this is basically the mass of the fluid, and rate of increase with respect to time, the mass of fluid will be with respect to time dou t, nothing but rho into dx dy dz. Okay, so this can be written as dou rho by dou t into dx dy and dz. Equating this equation as well as the net gain of masses in all the three directions, what do we get here is that equating, okay, equating the equation, we get minus dou by dou x into rho u plus dou by dou y into rho v plus dou by dou z into rho w into dx, dy and dz, that will be equal to rho by dou t into dx, dy and dz. Cancelling out these two, okay, what we get is this on the other side minus plus here and there, so we'll get d rho by dou t plus dou rho u by dou x plus dou by dou y into rho v plus dou by dou z into rho w. That will be equal to 0. So this is the continuity equation for 3 dimensions. Now let us consider few application here. If we have a steady flow or an unsteady flow, in a steady flow what happens there is, in a steady flow change of density d rho by dt will be equal to 0. Hence we can write this particular equation for a steady flow is d by dou rho dou by dou x into rho u plus dou by dou y to rho v plus dou by dou z into rho w, that is equal to 0. This is mainly because for steady flow. Steady flow, change in density is equal to 0. Now in a compressible flow, okay, in a compressible flow is another thing, that is in compressible flow in compressible what happens, the density will not be same, but in an incompressible flow what happens is the rho is constant, okay, rho is constant. So we can write this particular equation as dou u by dou x plus dou v by dou y plus dou w by dou z, that is equal to 0. This is for incompressible flow where the rho is equal to constant. Okay, now if we have to write the same equation, that is 3-dimensional equation in 2 dimension, here we will take w is equal to 0 here, third component basically we'll take it as 0. So we will be writing this equation in 2 dimension. 2d is nothing but dou u by dou x plus dou v by dou y, that is equal to 0.